Hello, everyone. Today, we discuss equilateral triangles inscribed in a square. The three vertices of the triangle are all on the edges of the square. As you can see, there are many such triangles. In this video, I'm going to explain how to construct these triangles and how big, how small it can be. I will also create another better animation from scratch to explain the idea step by step. Let ABCD be a 2 by 2 square. We want to construct an equilateral triangle PQR inscribed in the square. The easiest way is to pick the midpoint of a side, like the midpoint of AB as R. And then from R, we draw two sides of the triangle RP and RQ. So these two sides created three angles, 60, 60, 60. This way, we make the P and Q are symmetric on the opposite side. And you can easily see the triangle PQR is an equilateral triangle. It is also the smallest one. Why? In general, if P and Q are the opposite side, then PQ should be greater than or equal to CD, which is 2. However, in this case, PQ is parallel to CD, which means PQ is exactly the smallest number, 2. From the animation, we also observe that the midpoint of PQ is critical. We call it M. Go through M, we can construct any segment, reach the other two sides of the square. I call the segment P prime, Q prime. And then from M, I introduce another line which is perpendicular to P prime, Q prime. And this line intersects with the top side of the square as R prime. Then we obtain another triangle P prime, Q prime, R prime. We can easily see R prime, P prime, Q prime is isosceles. This side equals this side. Our goal is to prove that it is also an equilateral triangle. To prove that, let me connect M with R. By the construction, we know PM is 1, QM is also 1. And RM, the altitude, is square root of 3. I'm going to prove that triangle MQQ prime is similar to triangle MR R prime. This triangle and this triangle. We know they're both right triangles. To prove the similarity, we only need one more angles. Let's assume this is alpha, this is beta, alpha, beta. I'm going to prove they are congruent. So let's see, the rest part in the middle is gamma. Then we can see alpha plus gamma is 90 degrees. And this beta plus gamma, RMQ is also 90 degrees. Compare them to, you have alpha equals beta. We are done. The question is, what is the similarity ratio in this case? For example, hypothesis MR prime over MQ prime equals the size, current binding size is MR over MQ. MR over MQ is simply square root of 3 over 1, which is square root of 3. Now you can see R prime M divided by Q prime M. This divided by this is square root of 3. Then clearly we see R prime and Q prime is a 30, 60, 90 degree right triangle. So in other words, the whole big triangle P prime, Q prime, R prime is equilateral. That is our objective. Then what is the largest case? Of course, if P move down all the way to the corner or Q move all the way down to the corner, we obtain the largest one, something like this. This is C, also called Q1. And here is P1. And then we introduce a perpendicular line from M. We got it R1. Then P1, Q1, which is C, R1, will form the largest inscribed equilateral triangle in this case. Now, let's look at what is the essential part in this problem. Of course, M is crucial. Everything is turning around this point. P move up and down along a line, a vertical line. Q move up and down along a vertical line. And R move horizontally. So we have 4 important components in this diagram. M, 2 parallel lines and 1 horizontal line here. Now let's generalize the idea here. Assume we have 2 parallel lines and we have another horizontal line perpendicular to them. Of course, we can choose a point M so that we can draw in the middle of the 2 parallel lines and then draw equilateral triangle. However, here's the question. What happens if I choose another point. For example, I choose a point like here. This is my M. Then what will happen? For example, I can draw a line like this. I call this my P. This is my Q. And then from M, I draw a perpendicular line like this. I call this point R. Then I can connect PQR to create a triangle. Of course, from M, I can introduce another line like this. I call this point Q, this point Q prime, this point P prime. And then from M, I introduce another line perpendicular, which has intersection on the top line called R prime. This way, we have another triangle P prime, Q prime, R prime. The fact is that triangle PQR is always similar to triangle P prime, Q prime, R prime. The proof is similar to what we have for the square case. You have to prove two pairs of similar triangles. In the last part of the video, I'm going to create another demonstration which is simpler but nicer to explain the idea. First, I'm going to define my crucial point, which is M. Let's coordinate to be 0, 0, the origin. That's my M. And then two vertical lines, it's X equals -1. And another line would be X equals +1. Okay, let me hide the axis. Now, I introduce a variable, I call it T, to be 0. The system assigns the variable at the range from -5 to +5, which can be adjusted, but I will leave it as it. Then I define my first node of the triangle P. The X coordinate is -1, Y coordinate is T. It's my P. And the Q has X coordinate +1 and the Y coordinate -T. So as you see, when T is changing, P and Q is moving along the lines. Okay. Let's solve. Now let's find R. We know PQR should form an equilateral triangle. This can be implemented this way. I define a circle, center as P, but past Q. The system gave the circle a name, small c. And then I create another circle, center as Q, past P. This circle has name D. Now, I want to find their intersections. Intersect the first circle C, the second circle D. There's two intersections. I just want one of them, either 1 or 2. 1 is on top, okay, 1 is good. I define that point as R. R equals this guy. Now, let's connect PQR to form a triangle. This can be done using Geogebra command polygon. You know, the P, Q, R, O, O, R. That's it. So we can hide the circles and we can also hide the grid. Now, when PQ is moving around, you can see R is moving horizontally. And the equation for the trace of R would be y equals square root of 3. You see, R is moving exactly on that line. Now we can bring the circle back. This gives you the whole picture of the creation. That's all I have today. Thank you for watching.